Hi everyone, Mr. Boltri here, bringing you video 3.7, where we're going to talk about conservative forces. So first we're going to talk about what is a conservative force, then we're going to talk about properties of conservative forces, the relationship between the conservative force and potential energy, and then we're going to talk about negative work and what it means to have the negative derivative of potential energy. So first, we're going to talk about what is a conservative force. And I don't mean the political ideology. When we say conservative force, we mean that a force in which the mechanical energy is conserved. So remember, mechanical energy is just defined as the potential energy plus the kinetic energy, and conserved is a fancy word that we use for it doesn't change over time. So while the kinetic energy may turn into potential energy and vice versa, the total mechanical energy does not change. Uh, Compare that to a non-conservative force, which is pretty obvious, in which is a force in which the mechanical energy is not conserved. So an example of a conservative force would be, for example, if I were to take something and I were to hold it up and then drop it, it would then be subject to the force of gravity, and the potential energy that it had would all turn into kinetic energy, thereby not changing the mechanical energy. So the force gravity and force spring are two examples of conservative forces. Whereas some examples of non-conservative forces would be, for example, if a car was driving along and then it hits the brakes, and then it's subjected to the force of friction. Well, it had kinetic energy before, and then that kinetic energy is dissipated into the surrounding in terms of like thermal energy and heat energy and sound energy, which are not under the category of mechanical energy. That's not like potential or anything. It's not potential because we can't pull them back into our system. Once they spread out to the surrounding, the word for that is dissipated, and we can't get them back into our system. So examples of dissipated energy include heat and light and sound. So that would be an example where mechanical energy is not conserved. Or, for example, if I were to lift up my water bottle, thereby raising its gravitational potential energy, or throw my water bottle, thereby changing its kinetic energy, I would not be conserving the mechanical energy of the system. So the one thing that you'll notice with these conservative forces is that when we look at gravitational potential energy, force gravity, and force spring, is that those are the forces associated with the potential energies that we've talked about. And this is not an accident, is because the way that we talk about and define conservative forces has to do with the fact that the mechanical energy is conserved. In order for the mechanical energy to be conserved, it has to be changing from potential energy to kinetic energy. So we need to have a force that is associated with a potential energy. And it's just sort of like how we've defined these terms, is that if something seems to have a potential energy associated with it, then it is a conservative force because it can then use that potential energy to turn into kinetic energy and vice versa. But for example, there is no potential energy of my hand. That would just be me using my energy and adding it to the system of the water bottle. So that's why force applied is not a conservative force. So with these conservative forces, and I'm going to talk mostly about gravity, but springs work pretty much exactly the same way, is the magnitude and the direction of the conservative force, for example, force gravity, depends only on the location of the object. So for example, the water bottle here is going to have less potential energy than the water bottle here, because remember, gravitational potential energy has to do with the height. So it has to do the location of the object. When I change the location of the object, I'm going to change the potential energy of the object. So this is important because we don't care. It does not matter uh, the velocity of the object. So my water bottle right here has a certain amount of potential energy. And if my water bottle was falling and was in the same position, yes, it would have more mechanical energy because it would have the potential energy plus the kinetic energy. But in this exact location, doesn't matter if it's stationary, doesn't matter if it's falling or raising, when it is in this position exactly, it has a certain amount of gravitational potential energy. And that is because the force of gravity doesn't depend on the velocity of the object. Similarly, for a spring, the force of the spring has to do with how much it is stretched. It does not have to do with how fast it's going. So the only piece of information we need to know in order to know the force of the spring, and therefore the potential energy, the elastic potential energy of the spring, is how much the spring is stretched. We do not need to be given information on velocity. And that's important and very critical to solving problems involving conservative forces. And the last important point, and this allows us to really take a lot of shortcuts, is when we're working with conservative forces and looking at work specifically done by a conservative force, we only care about where it started and where it ended. So my water bottle starting here and ending here, we can just look at the starting and ending position. We don't care if it went all the way around or did sort of a zigzag pattern in between. All we have to look at is where it started and where it ended, and then figure out the difference between the positions, which then gives us information about the gravitational potential energy, and therefore information about the work done by the force of gravity or force of spring. And remember, this only applies to conservative forces. So the same cannot be true to say the work done by Mr. Boltri is only the work done by gravity, because gravity is a conservative force. So let's talk about the relationship between the conservative force and the gravity or potential energy. So if the conservative force we're talking about is gravity, then we're going to talk about gravitational potential energy and so on. So first, let's just remember a kind of basic definition of work. And work is the integral of force over a displacement. And then just by the definition of something being conserved, or the energy being conserved, the kinetic energy plus the however much it changes equals zero. So if the kinetic energy goes up, gravitational potential energy has to go down to balance it out, and vice versa. So we could just rewrite this as the change in kinetic energy equals the opposite of the change in potential energy, because like I said, one goes up, the other goes down. So if we remember the network, the kinetic energy theorem, we know that the network equals the change in kinetic energy, which we proved in a previous video, which if we look at only the work done by the conservative force, then the network becomes the work done by the conservative force, like the work done by the force of gravity. And over here, because it is a conservative force, we know that the change in kinetic energy equals the negative change in potential energy. Okay, this is all really important stuff to set up where we're about to go, because remember, our goal is to find the relationship between force and the potential energy. So instead of this work, the conservative work done by the conservative force, let's do the integral of the conservative force through the displacement that is doing that work. That's still going to equal the negative change in potential energy. So we know change is final minus initial. So this is just the negative final potential energy minus initial potential energy. And so then we can solve for the final and solve for the initial. But what I want to do right now is I kind of want a bigger picture of the relationship between these. I'm not trying to solve a problem right now. So instead of doing the final potential energy, what I want to do is I want to look at how the potential energy changes over the displacement. So I'm going to write this as a function of the displacement. So the force, which is a function of the displacement, because the force sometimes depends on where it is, like with a spring, and then how that affects the potential energy with respect to displacement. So then, to get rid of this pesky integral sign, I'm just going to take the derivative of both sides. So if I take the derivative of the left side by one of the fundamental theorems of calculus, I just get the force. And if I take the derivative of the right side, well, this is defined as a function of x. And this, the initial energy, is a constant depending on whatever initial energy I said I started the problem with. So the problem has to start somewhere, and that's just going to be the initial energy, which for this problem is going to be a constant, and any problem you choose is not going to change as we move the object around. This is just wherever it started. So the derivative of this is negative du dx, and the derivative of a constant we know is 0. So then we get the force, the conservative force, is equal to the negative derivative of the potential energy associated with that force. So what does that mean? We're going to talk about, well, what does this mean? How is this equation useful? But first, before we talk about if it is useful or not, let's make sure that it's true by checking it against the conservative forces that we already know. So if we look at the gravitational potential energy and then take the derivative of that, we actually end up with the force of gravity. So that checks out with what we already know. And the same thing is true of the spring potential energy. Just by our derivative rules and the power rule and everything, we get the Hooke's law. We get the force of the spring is negative k times the stretch. So this is, I think, pretty cool, because this shows that, like, yes, this law, which seems kind of random and not sure if it's true or not, actually does hold with the formulas that we have figured out so far. Which makes sense because we derived the equation for elastic potential energy by integrating the force versus stretch graph. So it would make sense that if we can integrate this to get the elastic potential energy, then we should be able to take the derivative of the elastic potential energy to get the force. So that's sort of how they're related. So to close up the video, I want to talk about negative work just because I feel like I should have mentioned it like 3 videos ago, and I'm going to mention it now because I didn't mention it then. So negative work is possible to have negative work, and negative work is just the energy that leaves the system. In this, I'm not changing anything that I've told you so far because if I were to hold my water bottle and then lower the water bottle, energy is leaving the system because the potential energy is going down. So the force that I am doing is the normal force, which is acting up, but the displacement is down. So the angle between the force and the displacement is 180 degrees. And the cosine of 180 degrees is -1. So that's going to, just given my force normal, that's going to help us end up with a negative work, which explains why energy was leaving the system. So I just kind of wanted to throw that out there. It's not really related to what we were just talking about, but I just wanted to clarify in case anybody's seen any problems where they've had negative work and they've been like, what's going on with this? And negative work is just energy leaving the system. And it happens when the force and the displacement are in opposite directions. So for example, the most common example of negative work would be the work done by friction, because if an object is moving to the right, the friction is acting to the left, which is in the opposite direction, which is causing energy to leave the system due to the work done by the friction. Okay. So, but more relevant to the discussion that we were just having is what does it mean to have a negative derivative of potential energy? What does that mean? So in order to talk about that, let's look at a graph where I had an object and I dropped it. It fell, thereby causing the kinetic energy to go up, 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 and the potential energy to go down, 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 because we can see in this example that the mechanical energy is conserved. So first of all, we have to remember, what does a derivative mean? And hopefully your calculus teacher has beat this into you by now, and that means the slope of the tangent line. So if we look at my potential energy curve and look at the tangent lines, we could draw a bunch of tangent lines, and we could see that all of them are negative. So what does it mean to have the tangent lines be negative, negative, negative for this potential energy curve? Well, so what that means is that potential energy tends to go towards 0. Just because an object wants to sort of be on the ground. If we drop something, it wants to be on the ground. If we release it in a spring, it wants to go back to its equilibrium point. And so this is just another way of saying that the conservative force, because we know that the negative derivative equals the conservative force, pulls the object back to its equilibrium point. So that is going to wrap up my video on conservative forces. We're going to do examples of problems involving conservative forces so you can sort of see the questions they're going to ask and how they're going to ask them in our next class. And then in our next video, we're going to really look at, if you were given a graph of the potential energy, how can we analyze that and figure out what's going on in terms of the forces and the motion of the object. But for now, this is Mr. Boltri wrapping up video 3.7. Let me know if you have any questions. And as always, go Bears.